Can you see my screen, all of you?
Yes.
Perfect. Here we go then. I just so today we're going to look at corrosion and protection. You've seen this slide before, and what we're going to really look at today are ways of preventing corrosion from happening. So in the introduction, I went through this already once, but I'm going to go through it in more detail now with some aspects I haven't covered previously, which you need to know about. So the famous statement, if it can rust, it will rust, is always true. There's always going to be the possibility of rust with iron, and corrosion if it's another metal like aluminium or titanium or other alloys. And in the big bubble, we have some preventative measures which we could take for preventing corrosion and also for preventing rust from happening. The obvious one is to paint the object. And then we can do something which is called inorganic conversion coatings, whereby we put a thin film of an inorganic material onto the surface. A very good example of that would be to phosphate. And then we can paint on top of that. So this inorganic conversion coating is actually an intermediate layer. You probably wouldn't actually see it in practice because it's covered up with a layer of paint, for example. Then you can have metallic coatings. These are things like galvanizing, which we've already looked at, or tin plating, which we're going to look at today. And then plastic coatings, where you put a plastic coat onto your metal object and the plastic prevents it from corroding. This may be a transparent plastic film, which you can't actually see very easily. So that's the big bubble. The little bubble underneath the blue one is two methods which we've mentioned before, but you need to know more about now today. And that is one called cathodic protection, and the other one is called anodic protection. And then in the red bubble, we have something called inhibitors. And an inhibitor is something you might put into the liquid that your object is in contact with, or you might put it onto the surface of the object itself. And the idea is that it slows down the corrosion rate. It may not stop it altogether, but it may slow it down and therefore inhibit the process of corrosion. So let's look at paint films first of all. You've already seen this slide previously, so it's obvious what painting's about. I'm not going to explain the actual process of putting the paint on. It's more of a question of what type of paint do we use to prevent corrosion and what kind of applications would need to be painted. So generally speaking, anything made out of steel, especially plain carbon steel, will almost always be painted for its application. The only real exception I can think of that is a railway line, which I mentioned to you previously, which are on purpose not painted. They don't need to be because they are designed to go rusty in the first place. But generally speaking, we don't do that, especially with a pipeline. So there are many different types of paints, and I'll mention some of them now. So paint film types, there's those based on solvents. These are the classic paints, what we call oil paint. They're based on oils which dry. So for example, if you take linseed oil or linseed oil, which you probably would, certainly in the old days, have painted your house with, and these days it's used in specialist applications. But something like linseed oil is a type of oil which, when it gets exposed to air, it oxidizes and it dries hard and it forms a protective coating. So most oil-based paints are based on this idea of mixing a liquid oil in with your pigment, which gives it the color and the body. And then when it's exposed to air, what we call the drying process, the oil itself reacts with the oxygen in the air and creates a film which then cannot come off, at least not for several years. So that's the solvent-based one. The aqueous-based ones are rapidly replacing oil-based paints because, as you probably noticed, there's a lot of health and safety concern about the use of solvents in any application. So oil-based paints, the traditional ones, are now rapidly giving away, especially for household use, into aqueous-based or water-based paints. And these work slightly differently in the sense that the water, which is the solvent, just evaporates. It doesn't do anything. It just disappears, leaving behind the binders and plasticizers, which are the body of the paint. And then underneath that, we have what we call epoxy-based paints. These are paints which are made in two parts. And the idea is you mix the two parts together and stir them up and blend them. And then the two parts react with each other in a chemical sense. The chemical bonds are formed. So this is not a drying process. This is a curing process. And curing is not at all the same thing as drying. So the epoxy-based paints, when they cure quite hard, it has to be said. And they are very, very durable, far more durable than the other two types of paints I just mentioned. But they are very expensive. So you generally use these on applications which only need that extra durability. For example, painting the hull of a large ship might well use epoxy-based paints, or something that's exposed to aggressive environment. So therefore, the composition of paints, there are three different things that go into a paint. There's what's called the vehicle. This is the liquid part, in other words, the solvent, or it could be water in an aqueous-based paint. So that's the first one here. Underneath that, we have the thing called the pigment. And this is what primarily gives it a color for a start. So if you want white paint, you're almost certainly going to have titanium dioxide in there because that is the main constituent of white paint. But you may also have zinc oxide in there, which is used for corrosion prevention because it contains zinc. And you already know that anything with zinc in it is going to be quite protective. And it might also, and very often does, contain ferric oxide, especially if the paint is red in color. And this is often used as a primer on steel for obvious reasons. Ferric oxide is in effect rust. And if you put that into the paint in this way, you can actually protect the underlying steel by putting the rest there beforehand in a very controlled way. And therefore we use ferric oxide for this purpose, and it works very well, it has to be said. And then we have something called polymer. And this is in effect the binder. It's what holds the paint together. It's what makes the paint paint. If you didn't put the polymer in there, all of this would just fall off and flake off. It wouldn't do anything. In fact, the iron oxide would indeed become rust. The whole point of putting the polymer there is to bind all these pigments together so they stay on the surface as the film for as many years as possible. In the case of a house, it's probably going to be 8 to 10 years, for example. On a boat, it could be a similar period of time, 8 to 10 years, for example. And these, I just mentioned linseed oil, which is the old traditional type of oil. It dries because it reacts with oxygen, as I just said. But today we tend to use polyurethane style pigments or polymers, which also react with oxygen to polymerize. But they don't have some of the problems that linseed oil has. In particular, just to mention, linseed oil is extremely inflammable and can catch fire easily. So it's not fireproof. And then typically speaking, the perfect paint film would be typically between 50 to 100 microns thick. In other words, 0.05 to 0.1 millimeters in thickness. That gives you an idea of the thickness of the paint. And generally, you want this to be as thin as possible because then the same amount of paint can be spread over a larger area. Also, we don't want to have any cracks or defects in the paint. We want the paint to be a perfect film. And if it's a metal component, which is generally what we're talking about in this course, then we want to completely cover it, especially in the bends, the folds, and the joints. So this is the perfect paint film, but in practice, real paint films are not like that. Unfortunately, the thickness does vary quite a lot depending on how you apply it. And also they're not completely perfect in the sense that water can permeate, or in other words, diffuse into the body of the paint and even get right through to the other side of it. So if water goes through the paint film, it will bring oxygen with it. And therefore we can have a corrosion situation happening quite quickly. So this is one of the biggest problems with paint films, is to stop this from happening. How do we do that? And in many cases, we can't. We simply have to accept the fact that it does happen. And as a result of this permeation, we get cracks formed and we get imperfections. And eventually, after a period of time, let's say 5 or 10 years, probably even less than that, in the case of a car, it might be only 3 years, the paint film will itself oxidize and it will start to peel off. It'll become brittle and it will no longer have any stiction or adhesion to the surface of the metal you painted, and it will come off. Just to mention, one of the reasons we put a primer onto metal is to avoid this problem. If you do not put the primer on first, then you're going to get this problem of peeling off quite quickly. If you put a good primer on, then the peeling off effect might take several years before you start to see it. The most enduring type of paint that you can get these days is the epoxy type. As I just mentioned, the twin pack, the ones you mix together, because they are much more durable than the regular paints because of the way the cross-linking occurs in the polymerization process. And sometimes these have names. They might be called coal tar epoxy, for example, because they're made from coal tar. And so what is the function of the pigment? Number one is to make sure that the oxygen cannot get from the air side to the metal surface. So that's why it has to be of a certain thickness. If the paint film is too thin, then it doesn't provide very much protection against the diffusion of oxygen. So we need to avoid this. And of course, the pigment itself provides the color and the aesthetic appearance. In other words, the style of the object, the color, so on. And also the surface finish, whether it's shiny or matte or something in between. The main failure mechanism is what we call debonding, which generally is the formation of blisters or bubbles. And this is due to the trapping of moisture or water underneath the film. I've already given you some examples of this happening previously, but I'll mention one or two more. And this often causes a change in the pH. Usually it becomes higher. Inorganic conversion coatings, what are those? Well, these are where we take the underlying metal and we treat it in some way, either with aluminium or phosphating, adding phosphoric acid or phosphates to the surface. And when we have a steel object, which is primarily made of iron, then this phosphating process is quite often used. So let's move on to some pictures now of some paints you might come across, because it's very important to understand the practicality of this. What kind of paint would you choose and where would you get it from? So some of them even have the name rust protector on them. So these are industrial paints I'm showing you. They're not the kind of paint you would use in the house. They're the kind of paint you would use for an industrial application where you want to protect something against corrosion. So they therefore often have the word rust protector. This one's a primer. Remember what I just said a moment ago. The first thing you do with a metal to protect a metal with paint is, first of all, you put the primer coat on first. If you do not put this on, you directly put the top coat on, you're making a big mistake, because you can be sure that the top coat will not stick properly. So the primer, this is just one particular example, does two things. First of all, it may contain materials such as, if I go back here, it may contain this phosphating compound, for example, in the primer itself. Normally that is the case. So you put the primer on to protect the metal with, let's say, a phosphate coating. And then it also provides a good surface for the main paint film to stick to. So instead of the main film sticking to the metal directly, it sticks or is adhered to the primer. And then some of them have this word oleum in them. And this is quite common for these industrial type paints. It means that they're oil based. These are solvent based, in other words. They have a solvent in them. They are not water based. And particularly important are marine paints that you would use to paint a boat with. And I'm going to say a little bit more about that now, because it's quite common in your application to be dealing with a boat, especially here in Norway, where most people have boats of one form or another. And if you get a job in the offshore industry or for one of the boat constructing firms, this is something you would need to know about. So I'm saying a little bit more about it. First of all, they can come in any color you like. There's no problem putting color pigments into a paint, so you can choose your color. And if you're going to put several coats of paint on your boat, you may choose different colors for each layer, so you can see which bits have been painted beforehand. This is quite an important thing to know when you're painting a large object, is to know what was there beforehand, because it's not always that obvious. Here we have an epoxy-based one. This is a two-part marine paint, epoxy anti-corrosion coating, it says. And here's another epoxy one. This says metal shield on it. It's designed for if you look at the picture here, it's designed for painting onto wrought iron, to be exact, a gate or post or something like that. Now here's an example of painting a boat. And if you can see in here, you can see two different colors here, which is quite common. Here's another, also two different colors. Actually, in this particular case, the person is polishing the paint. So what we're showing out here specifically are two types of paint. One is called a gel coat, and the other one is just called marine paint. Marine paint is a paint that, if I go back, for example, something like that, it could be an epoxy-based paint. And then on top of that, or maybe instead of that, you use a gel coat. And a gel coat is also a two-part mix, which has a shiny surface. In other words, it looks like a gel. That's why it's called a gel coat. Because it has a shiny surface, it can therefore give extra protection for the boat. In particular, it can stop the formation of barnacles forming on the hull. In other words, the part of the boat which is underwater. I've given a little chart here which shows the pros and cons of different types of gel coat versus marine paint, and you can read this in your own time, but just give you an idea of what types of parameters you might be looking for. You can also find, if you look, it's not difficult to find instructions of how you put your paint on. And this is just one particular instruction I got from a company that makes paints. And we have the underwater part here. And this is the waterline part here. And this is the bit above the water, what's called the freeboard, the boot top, and the underwater hull. And when it comes to corrosion protection, we are particularly concerned about this part, the pink part here, as to what type of paint should be put on there. And you may use different paint here, and yet another type here, and yet a third type here. So they may not be the same paint, and they may definitely not be the same color, usually not. These are designed to show different colors. That is normally what we do. And just to take the pink part in a little bit more detail, what we actually want to try to do when we're painting the underside of a boat, apart from giving it corrosion protection, we also want to try to avoid the growth of marine creatures, like especially barnacles and polyps on the submersed part of the boat, because this will cause a rough surface to appear on the boat, and it will slow down the boat when it's moving along, especially a large ship. And this therefore will reduce the speed, it will increase the fuel consumption and make it less economical to drive the boat across the ocean. So therefore, anti-fouling paints, as we call them, are very important. And so here's another example of a boat that's being in the process of being painted. And we're using two different colors here in order to show which part we painted previously. So we're painting a blue on top of gray in this particular case, and the job is not yet finished. And this is a hybrid paint system, meaning that we're using two different paints, one on top of the other. And the outside painting will almost certainly, and certainly in a large boat like this, be an anti-fouling paint, which stops the formation of barnacles. So here's another example of the kind of process you might want to do. Apart from painting the boat, you also want to clean the propeller, and the propeller is not painted. The propeller is made out of bronze normally, and bronze doesn't normally corrode, at least not very easily or not very quickly. Bronze, hopefully you've looked at bronze in your materials part of this class, but if not, bronze is an alloy of copper, and it normally contains tin. So bronze is typically a copper tin alloy, but it might also contain aluminium and other additives. Bronze is therefore used here, and you can see these people here, they're actually cleaning the propeller part, but you can see that the paint has already been applied to the main part of the hull. You can see this bright red paint. It's an anti-fouling paint. They probably look like this in the start. So where you have the anchor mechanism and anything that's going to be moved around, propeller being a good example as well, you're always going to get rust concentrated in these areas. So you need to have special paints in this area to stop the rust from forming. So a little bit more about anti-fouling paints. You can see I've written the word, oops, I can see I've written the word here. Generally, they contain copper. Now, why would you do that? Well, copper is quite toxic, it has to be said, to marine animals and growths. And therefore, if you put the copper on the boat, then it will stop the formation or the growth of marine creatures on the metal itself. You certainly don't want to get a barnacle here or many hundreds of barnacles, because otherwise that will slow down the boat as it moves along. But you need to take into account the fact there are very strict rules these days regarding what you can put into or put onto a boat and what you cannot put on. And therefore, the anti-fouling paints come under a very strict code of practice, which means that they're not allowed to dissolve in the water, because otherwise a toxic chemical, in this case copper, would go into the water and then will harm the sea creatures living in the water itself. And this is not allowed anymore by international standards. So therefore, the paints have to have only certain compositions which comply with regulations. Moving on, sometimes with a ship, we actually don't use people anymore to paint large ships. We use robots. And this is a very good example of where a robot works really, really well. Because going back to what I said before, part of the problem when you're applying a paint is getting the thickness just right. And if you're painting it by hand, you're almost bound to put more paint somewhere and not enough elsewhere. So you get a haphazard, random painting operation going on. And this you want to avoid. A robot is so much better than a human being for doing this job. So that's what we do these days. Generally, on certain a large object, like a big ocean-going vessel like this, you use a painting robot. And then also to mention, I think I've shown you this image before, that even after you've painted your object, in this case, it's a car, then you might put a clear plastic film on top of the paint in order to give it much better corrosion protection and possibly make the car last for another 5 or 10 years before you start seeing any evidence of degradation or corrosion. So now let's say something, so that's paints, okay? I'm not going to say any more about paints per se, but of course you can ask me questions if you want. Then there are other things you can do to protect metal apart from just painting them, and these are called metal coatings. And we've already come across galvanizing when we looked at the galvanic series. So you know something about zinc and a little bit about coating of steel with zinc in a process we call galvanizing. And when you did the Jaeger gel experiment a couple of weeks ago now, you actually saw this in action. I made a video showing specifically the effect of galvanizing on a steel bolt. So you know about zinc plating. And I've also mentioned, but I mention it again, that zinc forms what we call a sacrificial anode, meaning it will protect the steel because the zinc actually dissolves away preferentially, and it makes the steel into a cathode. And therefore the zinc is therefore an anode and dissolves, and therefore this word sacrificial, meaning we are quite literally killing it, sacrificing it, in other words, to make sure the steel doesn't die on us and it remains intact. So the zinc dissolves preferentially to the substrate, as I've shown here. Another one which I've not yet mentioned, but I will mention now, is the process of tin plating. So here what we do, instead of using zinc, we use another metal called tin. Tin is an element which has a very low melting point, and it can be deposited onto steel to make a protective layer. And almost all cans that have food in them, what we call a tin can, at least in English we do, that tin refers to the tin plating of the steel. The can itself is made of steel, but it's coated with a thin layer of tin, metallic tin, to protect it from corroding, especially on the inside if you have food in it. And just to mention something about tin plating, by the way, is that one of the reasons they use tin in food industry to coat the inside of cans, like I just said, is because it does not impart any taste to the food inside it. So it wouldn't taste like it had rust in it or something. By the way, if you've ever tasted any rust, you'll know what it tastes like. Not very pleasant, but tin actually doesn't taste of anything. It doesn't impart any bad flavors to the food. So this is the principal reason we use tin plating as opposed to galvanizing. We would never put food into a galvanized tin, even though the galvanizing will probably protect it very well on the inside, because the presence of zinc would unfortunately make the food taste really bad, whereas tin does not do that. So that's the reason we use tin plating in the industry, and we do not use zinc. So this photograph here shows you actually the process of galvanizing. And if you look at the insert here, you see here's the steel object. And in this case, it's now coated with several metallic layers and also even a paint film. So first of all, here, this bit that's pulled up here is the layer of zinc, which is on the steel. And then something called zinc patina. This is actually a zinc primer, which is put on top of the galvanizing steel layer. So we have the underlying steel. We then galvanize it by coating it with zinc, metallic zinc. And then we put a primer which contains zinc, probably in the form of zinc oxide, which I just mentioned to you a while back. And then on top of that, we have another primer, this one here. This might also contain zinc oxide as well, but it might also contain other primer materials. And then we have the paint finish here, and green is the paint finish, that in this case it's green in color. Here you have the composition of the zinc patina. It's a mixture of zinc oxide, zinc hydroxide, and zinc carbonate. So that's this brown layer here. And it says here, a hybrid method corrosion protection formed by painting over hot dipped galvanized steel. So this hot dipping process is in fact the process of galvanizing. This is when we say we're galvanizing something, we mean we're hot dipping it into molten zinc. And here you can see these people doing just that. Here is a bath containing molten zinc, so it's quite hot. And these are the steel objects, and they're quite literally lowered into the liquid metal for a few seconds, and then they pulled right out again. And the metal will stick to the steel to form a layer. And as soon as it's pulled out of the hot bath, it will start to solidify or freeze over. And it'll form crystals of zinc on the surface of the metal. But most of the zinc goes back into the bath to be used again on another object. Down here, you can see the same thing going on, and we're now zinc plating some beams made out of steel. And the great thing about this method of galvanizing, because the zinc is liquid, it's molten, then when we drop the steel in, all the surfaces get uniformly coated. And in fact, it'll leave by capillary action, the zinc will suck into all the nooks and crannies and the gaps. So this is an extremely good way of protecting an object which may have many parts to it. And you can see there are several parts here. This is not a single object. You have a U-shaped part here and some bulkheads here, probably welded, I'm guessing. And then the whole lot is put into the molten zinc bath to galvanize it. And when you pull it out, you won't see any of the underlying steel at all. All of it, or 100% of it, will be coated. So this then can go into service life. It doesn't necessarily need to be painted, it should be pointed out. Sometimes we do and sometimes we don't. Most of the time, galvanized objects are not painted. And if they're exposed to the outside elements like normal air and water, they will last for many years. typically 20, 30, maybe 50 years of service life before they have to be replaced or recoated. Something about tin plating. Here's my tin can I just showed you a minute ago. So there we often use what we call hybrid films here, whereby we are putting quite a few layers onto the surface of the metal. In this case, it's steel. And the first thing that's going on in this case is an iron tin alloy. So tin is the basic material we're going to use to protect the metal. There's no zinc in this case, it's just tin. But the first layer we put down is an iron tin alloy. And then we put down pure tin. And this is probably done by electroplating. And then on top of that, we have tin oxide. And then we have what's called hybrid films. And these might be paint films, especially on the outside of the tin, where you might want to put the logo on, for example. On the inside, you obviously wouldn't put any paint on the inside. This is going to be pure metal protection. So tin plating is done by, generally speaking, we don't hot dip, although you can do it. Tin is often electroplated onto steel because it's more effective, it's lower cost, and it's easy to do. So I'm going to do another lecture probably next week even on electroplating. So I'm not going to say much about electroplating, except in this case, you need to know the effect of it. And the effect is that we take our, basically we have a bath. This is what the real thing looks like here, but this is my drawn diagram showing the basic principle. So we have a liquid, which in this case is the electrolyte, which contains a tin compound. There might be tin chloride, for example. And then we have an anode and a cathode. And the anode will dissolve and the cathode will be plated. So the anode may be made out of pure tin metal, for example, and the cathode is the object, the piece of steel that we want to plate onto to protect it. So there's in this particular case, there's a 4-part process. We start off by cleaning, and then we prepare the plating bath. That's what I've just described here, and this is the real thing. And then we do the electrode deposition process. And this might be in 2 parts. We might put down what's called a strike layer, a very thin starting layer. And then we put the main layer down on top of it, the thicker layer, which gives the ultimate protection. And in industry, we'll have a whole line of these. This maybe have 20 or 30 tanks, one behind the other, processing a lot of parts. You can't see the parts because they're inside the electrolyte. But in schematic drawn, they would look like this. Of course, we need a power supply. So the anode is positive and the cathode is negative. And I'll show you an example of this later on. So we will do electroplating specifically in another lecture. So I think that before going on to this, I'm going to take a break for, let me see what time it is. Yeah, it's bang on 1 o'clock. In fact, it's 4 minutes. But can we have a break till 1:15? Till 1:15? Can I have a thumbs up on that? Okay, so I'll stop the video and I'll upload it and we'll start in 1:15. Thank you.